Welcome everyone, and we are going to have Leonard Hall giving us a controls update all about S-curves, of course. And over to you, Leonard.
G'day everybody. This is this is a little bit of an overview of control in general, with a little bit of a update at the end on the navigation side of things. So I've attempted to give a bit of an overview of what we've done over the last 12 months and how that looks going forwards into 2020. And hopefully some interesting stuff in the last half of the talk on what we're looking to do in our navigation going forwards, and sort of some of the challenges that we've faced there. So moving from the motors deeper into the autopilot, we've through the year we've had a few sort of nice solid step forwards in the aircraft and our ability to control the aircraft. Early on in the year we did a thrust loss detection of the motors, where we look for significant slope across the thrust vectoring of the motors, which shows a strong bias towards one motor that is consistent with a serious thrust loss. And if we combine that with the motors, that motor maxing out where we're actually short on thrust, so we're coming down and we don't want to be coming down, we are going to this thrust loss detection state. And what that's meant is that when you lose a motor, the one that's sitting at the limit and pushing down the rest lower than they need to be gets ignored, and all of those the thrust of all of those motors across that surface lifts up based on the next highest motor. And that has a dramatic effect on the hex's motor out maximum thrust, of going from 33% up to 66%. So literally hex's thrust doubled when it lost the motor out situation. This is that 33% figure is the reason why hexes drop out of the sky. Even if they don't tumble, they lose altitude when they lose a propeller if they are relatively heavily loaded. With the octos, we went from 50% up to 66%, but that's that makes a big difference, especially on a low battery. The other big thing we did at the motors level is we separated the feed forward into the motors library. Now, plane and heli both already understand the significance of this, but multi-rotors have been somewhat neglectful of it because they don't actually require this feed forward in the rate. And this is particularly useful when your actuator output is approximately proportional to the rate of roll or pitch or yaw. By doing that and separating it, taking it into the motor library in a separate function, it allows gain scheduling to be done appropriately based on airspeed, or in the case of a single rotor or coax rotor, which is a lift band with moving actuators underneath it. It allows us to actually gain schedule the amount of movement from the feed forward differently to the PID, because they both need to scale differently to maintain the same dynamic performance based on your throttle position, for example. Perhaps one of my favorite things that we sort of just got in at the end of last year for 4.0. Actually, did we? I don't think it actually went into the latest release of 4.0, but it should go into 4.0, is ArduPilot motor order support. I'm not sure if I can't remember who actually did the legwork for us on that, but Randy probably knows off the top of his head. But no, thank you very much for that. That absolute godsend to finally have our own motor ordering that actually matches the propeller test and actually makes sense. And we've sort of been dealing with a hangover of what somebody did right back on the first implementation of when I first trying to get these things to hover and never and sort of been stuck with it ever since. So I'm sort of looking forward to slowly changing all my aircraft over to that and actually having the servo output, ESC output order matching my propeller order. So one of the things looking forward to 2020, the tricopter has had another, thanks to Josh and Eric, who've wanted to fly some tricopters, and rather, you know, they like flying aggressively, a lot of full throttle, and I think we've finally worked out tricopter properly with the way the tail rotor is handled, so we don't get this wobbling of the tail under full throttle and that sort of stuff. So that should go in this year. And the other big thing I hope from a motors perspective, because this is all done down in the motor mixers. The other thing is ESC telemetry based motor loss support. So basically combining the thrust loss detection, and instead of doing it based on a thrust balance and surface slope sort of metric, with the ESC telemetry, we actually should be able to categorically say this one's gone and remove a lot of the ambiguity. There's potentially moving forwards, as we sort of understand what we can do there better, to some options for partial thrust loss and things like that, but that's going to be a slower evolution of understanding. So attitude control or development has, you know, when you think something's all nice and sleepy, you know, sometimes just huge things happen and catches you by surprise. And the attitude controller has been one of those areas this year. Thanks to a very large degree to Andy and Bill, but and I think Tom. Oh, sorry. Yeah, the big things that have changed, and I think everybody's sort of starting to appreciate the significance of it now, is the dynamic harmonic notch filtering. That's been an absolute godsend. Basically what that does is it sets up a comb of notch filters that you can turn on or off, that is then moved up and down based on the lowest harmonic to match the RPM of your, or the average RPM of your propellers. And so that allows you for an X8, for example, to take care of the first harmonic, which is an unbalanced propeller, the second harmonic, which is your blade passage frequency, and your fourth harmonic, which is the interaction of the upper and lower blades as they pass over each other. For an aircraft using tri-blade props, you get the first, the third, and the sixth harmonic. And so being able to take those harmonics out at full rate directly on the output of the sensor before they come into the rate loops has made huge difference to our ability to handle that high frequency noise. That really, you know, very significant high frequency noise. The PID filter design has been enhanced and sort of prepared for a few things coming down the track. Now, what we've found is that as we get a really clean aircraft, we've got the harmonic notch filters, dynamic harmonic notch filters going. We've still got the original notch filter. And I think if you listen to Bill's talk, you'll understand why we kept that separately, because it's very useful for shaping some of our control gains to deal with various issues, and Heli has a few of them. So it's very helpful for Heli. But what we found is, as you make everything else, like you make a really clean aircraft with a really clean, you know, with very clean inputs coming from the IMU, you know, we're able to filter out all the harmonics of the propeller. We then get down and we start seeing things like the EKF, the noise coming in through the EKF becomes really significant. So the EKF doesn't have the low pass filter or the harmonic filter going, you know, on the data it consumes, and then works out what the angle is. So that angle is effectively unfiltered, and there's a bunch of reasons for that, but pretty much the EKF likes raw data, because then everything makes sense. If you start removing part of that data, then all of a sudden things don't make as much sense. And you know, Bill, I'm sure we could go into that a lot in the next talk. But the what we find is that a lot of we can take care of the rate loops, but then the attitude loops come in, you know, pass all that noise in. It's been integrated, so which is inherently a low pass filter, but it hasn't been strongly filtered. And so we've added a target filter, and I'll show you a diagram of that in a second. But we've also added a separate error filter and a determ filter, and I'll explain why that's quite important as well in the following slide. But this allows us to take care of a couple of other noise sources, including the raw noise that's coming in through the EKF gyro bias updates, which you know, brings some step inputs through, and also the RC input, which is happening at a lower rate. And so we actually see these steps in change of attitude, especially if you're moving slowly. It's funny, if you move quickly, you don't see this noise, but if you move slowly, you see this sawtooth thing in the error target as it tries to move up to the next step, the next increment on your RC input. And you don't see that in auto mode, for example, where we're actually getting a full rate attitude request. We've taken that feed forward support in the motors and actually fully acknowledged that through the rate loop, and separated that out and appropriately handled it during large attitude error correction. So if you flip your aircraft and it comes out, we actually shut down yaw and focus purely on rotating our thrust vector until we get our thrust vector back to within a window. There's no point worried about what direction you're facing if you're upside down. So get your thrust vector right, and then pardon me, Josh will understand why. Get the thrust vector right, and then focus on your heading. So that's looking good. The quaternion-based attitude controller, nobody has thought about it since it went in. It's one of those wonderful things where the less people recognize that you've had that you've made a change, the more successful that change is. So the quaternion based attitude controller, which is a huge change, has just disappeared into the past, and we haven't seen any bugs or anything like that. So that's, I'm really, you know, proud of that. That's happened so well. The tuning guide, we put out a really detailed step-by-step tuning guide that's based on what I do when I do industrial tuning. It just goes through step by step. This is what you need to do. That has received, that seems to have helped a lot of people, and it's definitely saved a bunch of my time because I haven't had to write it out over and over again trying to help people on the forums. But so that seems to have been a big step forward for us as well. Something that a lot of you probably aren't aware of, and the Paul Riseboroughs and Bills of the world will appreciate the significance of it. Bill's been using it for heli, and we've used it on Josh's heli to try and understand what's happening better, is the system identification mode. Now that places a user-defined chirp in and injects it into parts of the control system. And this is really useful for doing system identification work, where you actually, it allows you to actually create a model of your aircraft. And I'm highlighting that here because this is one of those things that I hope will really help get more universities involved and research institutions or entities that actually have the background knowledge or resources to do a full system identification, model-based optimization of PID parameters and that sort of thing. And I'm hoping that over the next year or two, we'll start to see insights from this ability to create these system models flow back into how we further improve our control laws, and perhaps it'll help discover a few corner cases that we didn't know we had. So looking forward to 2020, yaw and angle rate, your angle rate input for auto modes, and that will I'll perhaps talk about that a little bit more in the last half of the talk. But basically that allows us to pass both angle and rate of change of angle into yaw in the attitude controller. It's going to be, it is very helpful for a lot of navigation problems, and something Tridge and I were working on when we were looking at doing fast little circles in a chamber. So I would like, and this is one of those things that's going to require help from others, but I would like to try and get a generic auto tune, including feed forward tuning capability, in where now one of the critical things, I can do the auto tune. I've got the algorithms already there for the most part, and I've got tuning methodologies that have been shown to work well, that can be adapted into auto tune for feed forward. But the bit that's beyond my personal programming skills is the being able to point auto tune at a PID object, any PID object, and say, all right, this is what I want to tune now. At the moment, we hard code it for multi-rotors. And so we can't use it at all for tuning up helis, for example, because helis use feed forward and roll and pitch heavily, and they have a different filter and tuning methodology for yaw. So, all three axes are not usable. Auto tune can't be applied to all three axes. And what I'd like to be able to do is have auto tune take the PID object and maybe a parameter that's set at compile time in the PID, or something that the user sets in the PID, sort of says what sort of tuning approach to take for that PID, and auto tune then goes through when it's handed that PID, when you pull the channel 7 switch or change mode to auto tune, it reads that and says, okay, this is the methodology I need to use for this particular axis. And that then opens the way to potentially, if we start using those PID objects in plane, which should be more than possible, we potentially will have two tuning options that can be applied to plane as well. So the other thing, Bill, myself and Josh have been working on a feed forward D term and an attitude feedback lay term. Now, that's both of these things. The feed forward D term basically allows us to actually do a reaction based so a command D response going out to the actuators that is higher than what is stable in the feedback loop. So we're experimenting with that in Helis, and the feedback and the attitude feedback delay term is where we delay the attitude we take from the EKF by a small amount to account for the delay that we see through our system. And when we do that, we don't, so at the moment when you, initially you're zero, when you come up, you get this gap between where you want to be and where you are. The controllers then move that up to match during that maneuver. And then when you flatten off, you get an overshoot because there's a delay in its reaction again. This is, you know, this is an idea that was floated quite a while ago, but yeah, we yeah, at that time it was we didn't have all the rest of the stuff in place to actually really look at that seriously. There was a lot more low-hanging fruit, and so now there's that potential to start looking at that. So this is the general layout of our controllers. You can see the little delay crossed out there, but this is sort of the general overview of our controllers. The quaternion stuff is this little area in here, but we've evolved this. I'll show you a diagram of what this now looks like. But we've got our input translation stuff, and this might also come from either sticks or from the navigation controller, position controller. So this is where our input shaping happens. We then basically we take in a set of target rates that's then integrated to a target angle using quaternion maths, and then we effectively fly an acro in the controllers, and we remove this any accumulative error like angle error as we you know, over time. So we stay where we expect to be. But this is one of the this methodology of actually doing the primary control through the almost directly through the fastest loop has dramatic impact on the speed and our reaction time of our control. So this basic architecture that we've sort of developed in the attitude controller is what we're going to be taking up through the position controller. So this shows the fundamental difference in this filtering positions of roll and pitch in the error versus the D-term filter. So this is the error coming out of, you know, coming into our entire PIDs here. And in yaw, we actually place this low pass filter here, and we have a switch effectively that we can turn on or off that moves it to just the D-term or all of the terms. Now, the reason why this is significant for yaw is because yaw has a mechanical D-term in the form of the torque being applied to the motors. Yaw is by a long shot the fastest responding axis on a multi-rotor because it gets instant torque change, whereas roll and pitch need to wait for that RPM to actually change, whereas yaw, it reacts as soon as the RPM begins to change. And this low pass filter effectively changes the gain of our mechanical D-term, and we tune this low pass filter in exactly the same way as we tune up the D-term in roll and pitch. Like literally, we just pass this variable in for the filter frequency. This is something that I am still seeing most other multi-rotor controls have not worked out this simple aspect of multi-rotor control when I look at the yaw response on other aircraft. So you can see here that now with the new filtering, we have this D-term filter separate to the low pass filter. Now, I have found this really useful for vehicles suffering from high noise. It allows me to, another tool to knock off the high end noise. It's much better if that noise isn't there, but often when people come to me with aircraft, you know, they don't understand where they need to make improvements. And in order to get an aircraft flying and flying effectively, this filter has been really useful even on roll and pitch. And for really high-end yaw control, and I've only ever had to do that on one aircraft. These two, it was a racing aircraft, but these two filters come back into play with D-term, especially if you're dealing with aerodynamic bodies on racing aircraft, and they really can do with the extra precise yaw control. And this is the target filter, and this is everything comes from the rest of the attitude controller and the EKF and all that other noise, those other noise sources I was talking about. This just gives us an extra pole to reduce that high frequency noise coming through there. As I said, there tends to be a bunch of little step noises coming through, like little steps that create broadband noise coming through, but then there's also the unfiltered, it's got a low pass integrator on it, effectively coming from the EKF, but there's that's effectively unfiltered noise. So this being able to chuck this target filter on really helps reduce that. Down here we can see that this is changed a great deal, and this again was code that was just out of my league on being able to do it. And Andy was kind enough to get his teeth into it, and has well and truly been locked into being a dev now. But the dynamic harmonic notch filter at the end of this has been a big step forwards. Now, did I talk? Yeah, I think I can. I didn't. Oh, where did I put it? So coming up in 2020, this is going to be further enhanced. So like it's been progressing very quickly. Initially, it was just, you know, just the simplest implementation that we needed to get done, but it's just spiraled, and we're looking at double notches to increase the bandwidth of the notch as a potential option, and it works really well, but it's a complexity question. Andy's been working on a real-time FFT that runs in a background process that we can then actually choose that frequency based on the FFT, and we've been discussing an option where we define the FFT based on, but then do short-term changes based on the throttle value. So it's sort of a mix between the FFT and the FFT-based source of that RPM and the throttle-based thing. The other thing, we need to window where we look for that primary harmonic, and also using the throttle-based thing to make sure we get that window right is another option. But Andy's got a bunch of stuff already working on that in that area and flying on a bunch of small aircraft. This has done just awesome things for all those little aircraft out there, because those little aircraft require this low-pass filter to be set quite high to minimize the delay through this loop here. And so especially on these smaller aircraft, the choice of these two filters are very important. This loop up here is the feed-forward D-term, where that would fit in, and we're initially just looking to reuse the settings for the D-term filter on the feed-forward D. That may not be completely optimal, but we're starting out with something. You know, it's always good to minimize the number of parameters. And this is where, when I was talking about auto-tune, being able to just point at a particular set of these, you know, so for example, yaw, we tune P, P is equal to I, and we tune this filt E. This is set to 0. This is set to 0. For the PID, we tune PD primarily. I is equal to P. Your I is 1/10 P. Roll and pitch, we tune P and D, and these filter settings need to be set by the user. And we still haven't got a real solid methodology for setting these other than reaction time and the desire to preferably keep this at 10 and 20 hertz because the RC inputs at about 50 hertz. So there's still probably a bit of gains to be had in precise tuning methodology and how we actually make full use of these things. The feed forward is really simple in that we just, you look at how much output is required to move at what given rate, and then you can calculate the feed forward term straight from that. In an auto tune case, that's a little bit more complicated because we can't just sit there doing rolls, but yeah, the principle is there. The beauty of auto tune is we can take very precise measurements in short times and take multiple of them to average out a nice approximation of the ideal value. The position controller, that's actually been, it's always good when, I look at this and I see we've done bugger all in the position controller. It's a really good sign, and it's the sort of thing where, going back to what I said about the quaternion controller before, the less people acknowledge that anything's happened or talk about some aspect of the code, the better that, the better job we've done. It's a joke I sort of tell, with the S-curve stuff. It's like, if we get this right, it's going to make a huge difference, and nobody's going to notice because they're not getting pissed off with the last version of the navigation controller anymore. So we just hear less appreciation. We can say no appreciation is good appreciation. So looking forward to 2020, there's been a lot of work being done in the background as we do this S-curve stuff to update the position, velocity, acceleration PID objects in the position controller, and take a lot of the stuff we've learned in the attitude controller as that's evolved, and actually place it, making those objects consistent with the attitude controller, but also restructuring things to be cleaner, based on what we've learned in those PID objects. In particular, the Z-axis control law has a few hard-coded aspects to it, which make certain problems difficult to tune around, and so that'll be a nice relief there. But it will also open up things like old hold and position control, the position control PIDs to potentially be auto-tuned as well. We've improved EKF reset handling and limit handling in the attitude controller, and there's a few concepts there that we'd like to bring through as standard components of our control law design to handle those particular things. That the EKF reset handling, for example, is we just simply keep a record of our error, whereas that was just something we calculated on the way before. And it's really and if we have a reset event, we actually take our last error and our current EKF output and work out what our new target should be, and then we start the loop again and actually calculate forwards from there. And so that guarantees that an EKF reset can't create a twitch in the aircraft, and instead it creates the aircraft just thinks it suddenly moved, and the attitude controller then slowly moves it back to the to its original target position, as opposed to getting in this instant bang and this twitch and punch that we see go through the airframe. The other thing, and Paul will be happy to see this, the support for 3-axis feed-forward architecture for position, velocity, and acceleration. The idea of this is the output of the position controller comes down fundamentally to an earth frame acceleration vector. Now, at the moment, again, multi-rotor is very selfish, and basically it assumes you have a single thrust vector pointing up through the z-axis, and you rotate that around to do this this control. Something like sub, for example, has roll, pitch, yaw, and then it's got thrusters, so it can be upside down and cocked off to one side and still just thrust north. And so it allows a more generic vehicle-specific translation there. That would, potentially allow sub, for example, to run a 3-axis acceleration PID loop on its thruster, on its linear thruster actuators. The structural changes support, so that generic to acceleration attitude translation, but it's not just attitude, it's perhaps a 6DOF actuator output. There's lots of other advantages there. For example, when you're talking about aircraft that have got a lifting surface, like one of my aircraft, for example, is a multi-rotor with lifting surfaces on the arms, and it allows you to potentially come up with a system that changes the pitch of the aircraft to increase the lift off of those lifting surfaces during slow forward flight, as opposed to just vectoring the thrust. Navigation controller, there's been a few structural and parameter changes, and the cleanup stuff that Peter's been doing has sort of crept through there a little bit, and a few nice little things here and there, but fundamentally our fundamental core navigation algorithms have not been changed for years, which again, it's a good sign, but everybody knows there's a bunch of shortcomings there. In particular, when you go fast around a corner, a fast corner, you cut that corner dramatically. If you've got fast, the high maximum velocity and low maximum acceleration, you get this long leash, and basically you drag it around this rubber band. And so we control the end of this rubber band, and the aircraft is just this parachute on this rubber band effectively that follows behind. And so when you go around a sharp corner, the parachute cuts the corner. Oops. So, sorry, I just hit my, yeah. So moving forwards, we're going to replace that whole system with an trigonometric S-curve based system. Now, I actually got that, a few of you would have seen some YouTube videos that I put out a while ago, all victorious, yes, I've got it working. And I sort of went, okay, I can put this in. We've got to do splines. How do we do splines? And so since then, I've been trying to work out how to do trigonometric S-curve based spline segments. And I've only just learned how to say that properly. And I probably didn't anyway. But so that's been a bit of a win that I've only recently had, and I think I've got a solution now that actually does that effectively. And all this also follows into input shaping on guided mode and taking the same attitude controller architecture and placing and using it for guided mode. And so pretty much that means guided mode can potentially get an order of magnitude increase in reaction, in delay through the system, and allow companion computers to have much more, tightly coupled control of the aircraft, and all that sort of comes out of this work with improving our position controller and in response to a higher level requirement on the on the navigation controller. So, navigation controller in 20 minutes. so the navigation controller, I sort of went through a lot of this last year, so I'm going to give you a little bit of a cut down version of what I presented last year and sort of show you how that's progressed on with the curves. So basic thing with a navigation controller, first pass is pretty much just create these straight segments. Ideally, we want really smooth control. We want the aircraft to, you know, it's all about confidence. And an aircraft can hoon around, do a great job, but not inspire confidence. And so the secret to confidence, in my opinion, is the aircraft needs to look like it's in control. It's not good enough for it to be in control. It needs to look like it's in control. And a big aspect of that is the way it moves. If an aircraft goes, you know, and with these jerky movements, that may be the precise attitude it needs to get to, but it's not confidence inspiring. An aircraft, in order to be truly confidence inspiring, an aircraft needs to go, I need to be here. Thank you very much. I'm here now. And I did not, you know, I didn't need to move my motors much. There wasn't a big bunch, you know, I didn't shake the crap out of my payload, you know, and now I'm going to slow down. That's what gives the impression of control. That this is why the great Twitch hunt of bloody 19 of the year 18 was such a big deal, because people were seeing the aircraft going through a waypoint and doing this as it twitched. It's like, what's happening there? Is it going to fall out of the sky? So this really smooth reaction as we go through corners and through discontinuities in our waypoints is really important. And that feeds into especially our corner geometry, where we have this defined discontinuity in our waypoint. For things like helis that have got this really predominant, really noticeable tail on them, that happens to be quite a significant aerodynamic, surface back there with the disc of the tail. Coordinated turns through corners is really important. And again, that comes back into the other vehicles like Rover, for example, that has no choice but to be coordinated. And as I sort of said, free of any sharp discontinuities, not just in the corner itself, but the braking and acceleration into a corner. And so that's where S-curves come in. The S-curves are, so this is the normal S-curve, the normal linear S-curve. Now, what we see here on the left is we have, at the bottom, we have the jerk profile. Now, moving forward, so we have position. If you differentiate position, you get velocity. You differentiate velocity, you get acceleration. Differentiate acceleration, you get jerk. If you differentiate jerk, you get snap, and then crackle, then pop. So what we're going to be talking about here is position, velocity, acceleration, and jerk, and a bit of snap as well. But here we've got velocity, acceleration, and jerk. Now the jerk here, what this basically says is we're going to have a jerk limited response as we're looking to accelerate up to a velocity and then decelerate. And so in the end, we stop it. We've moved from one stationary position to another stationary position. Now, what you see here is we see a rectangular jerk profile, and that results in a slope on a limit in slope of our acceleration. If we didn't have this, we would just get a rectangular acceleration profile here. But this limit in jerk here means that you've limited the rate of change of acceleration up until you reach a maximum acceleration, and then you decrease your acceleration down here. And that results in a curved on your on the corners of your velocity profile. So we go from a rectangular jerk response to a trapezoidal acceleration response, and then we go to this curved trapezoidal velocity response. Now, when you realize that in a multi-rotor or a helicopter, this acceleration is our lean angle, and this is our rate of change of lean angle. Now, you can see a problem here is that we have an instantaneous rate of angular rate of change, or angular acceleration here, as we go to initiate a movement. Now, this is the dreaded twitch that we talked about. So in order to actually make an aircraft confidence inspiring, we need to actually not only limit the rate of change of acceleration here, which is really nice, because otherwise it would just belt it at whatever angle it needed to do that acceleration. We also would like smooth transients in our jerk response. So this is what we've come up with. Now, this red line here is the new jerk response. Now, this is a raised cosine function. So pretty much it's just a quarter of a cosine lifted up, so its negative most point is 0. And so the function, so this is the key function that all of this stuff is based on, and you can see it's just 1 take cos, the peak jerk divided by 2, because this goes from 0 to 2 as you go from 0 to pi. So this is what all of these results are based on. And you can see, and this becomes our response now. You can see that the jerk now isn't a square, isn't a rectangular thing. It actually looks like the velocity profile we saw earlier. The acceleration, although this slope here is consistent as it was before with our peak jerk, it's got these nice rounded corners, and you only see the first part of the velocity shape here. This is just the acceleration, the change in velocity graph. But now if you think of this as your lean angle, you can see that we accelerate into a rate of change of lean angle. As we approach our new target lean angle to achieve that particular acceleration, it rolls off and slows down and stops perfectly at that new lean angle. And our acceleration our angular rate also accelerates up and is nicely curved. And this, the jounce or snap, is, you can see that the acceleration of our attitude is nice and smooth as well. So this allows us all the way down to that fundamental parameters of the attitude controller, define navigation curves that are achievable by the autopilot. We can look up that ATC accel limit and define what a maximum jounce or snap is. This jounce, snap, it's the same thing. Same with our, we can define our maximum jerk based on our maximum roll or pitch rate that we're allowed to achieve in the attitude controller. And our maximum acceleration can be directly taken from our maximum lean angle that we allow. And so you can see how that that we are looking to create a kinematic shape to our progression from A to B that is completely consistent with what the vehicle can actually really do. So that's fine for sort of getting into a straight line, but corners, we saw this yesterday. Let's go around a corner. Well, that's what circles are for, mate. Now the problem with circles is they are not smooth. They're only smooth in that, when in the position. you can make them smooth in velocity by keeping constant velocity. But then as soon as you get to accelerations, as soon as you enter the corner, you need to create an instantaneous radial acceleration to go around that corner. So you get this square acceleration response, and then you get these massive jerk spikes either side as you go around the corner. Corners are actually really quite tricky, because we need, there's a whole heap of requirements for a corner, for a simple corner between two straight segments. We need to be able to come in to and pass within our corner radius. So we need to be able to say, look, you know, we need to navigate really precisely. Oh, you know, you're just close enough, good enough. You know, as long as you're within 10 meters, you know, barrel on through. It might be you have to be within 20 centimeters of these things, because you're navigating in a confined environment, or you know, you're doing some really precise work. The other thing is we need to, you know, if we've got these different corners, we need to slow down for a corner. We need to, we don't want to slow down too much. We want an optimal corner. So we need to slow down to a point where we can go around the corner, meet all our requirements, and then accelerate out again. Ideally, if we want to make a coordinated turn, we'd like to have a direct output of our turn rate at any given time. We'd like to know what our maximum turn rate is. So perhaps we can limit our corner speed to our maximum yaw rate, so that we can actually maintain a coordinated turn all the way through that corner. And you know, so obviously, you know, it needs to come in from a particular angle, go out on a specific angle, and then transition from whatever your maximum velocity is along those legs down to the maximum corner velocity you can maintain while obeying all your rules. So this is what I presented last year. We end up with curves like this, with the acceleration and our velocity slowing down and speeding up. Now what that looks like is something like this as we go around these corners now, and you can see that the green line showing the braking acceleration, the light blue showing the cornering acceleration, and the dark blue showing the magnitude of the velocity. And you can see that the aircraft slows down as it comes into the corner, goes around the corner, it rolls into the corner and rolls out of the corner, and you can see the braking velocity, the braking force increasing as it enters the corner, backs off to zero as it goes into the corner, then smoothly accelerates out of the corner. And so this is literally close to the perfect corner. So this looks great in the air. You can change the velocity and it will follow precisely the same track through the corner. It's sometimes if you're going slow below your maximum corner velocity, the corner will get a little bit tighter in that corner, but that just means that you get close to that waypoint corner, but it never goes further than your waypoint radius. So it's a really well-defined corner geometry. And so this is the jerk cell velocity, and as you can see here, we're able to predict ahead of time what our maximum turn rate is. And you can see even our turn rate, you know, accelerates into the turn, reaches a maximum turn rate, and then decelerates out of the turn. So really happy with the way that actually manifests itself in the way the aircraft flies around a course. A dramatic improvement for our linear waypoints. And then we got to splines. Splines almost killed me. Splines are basically made up of multiple segments, and so you have two waypoints, an entry and exit waypoint. You have entry and exit vectors, and you define a curve as if you had you know, grabbed, if I'd been prepared, if you there we go. If you grab, you got 2 points, you got 2 vectors, and you bend something flexible around there, you know, you get sort of spline curves, right? So It allows, you know, so ends of a survey mission, you could just do a spline, it would create a nice curve over the top. Ideally, we would go through that spline at close to the maximum velocity the aircraft is capable, given the acceleration limits and, you know, jerk limits, etc. We should never exceed our kinematic limits specified, you know, WP, NAV, max excel, things like that, or max jerk. You know, we should you know, this should be twitch free. So these are a couple of examples of, you know, this is sort of how we ended up calculating these things for the S-curve based implementation. We break it into 3 vectors and a joining vector. These vectors here are equal in length and 3/4 the distance between the waypoint. Initially, it was equal to the distance between the waypoint, but that had a couple of little kinks that were not pleasing. So we reduced that down to 3/4 this length. And then a third, this B segment that connects the end of those two lines. But then when you actually flip this over, this B then comes back on itself really dramatically. And so what we do is we limit that B segment to being vertical, and then these segments equal but less than 1/4 of the waypoint to waypoint distance. And so that's the basic formulation. And then we link these using just the raised cosine segments of the spline, none of the linear segments. So this is always accelerating somewhere if it's in a corner, or the jerk is always positive. It never reaches a linear constant state through these corners. And so the idea is we want to maintain a turn through this whole geometry, this whole path. And so this is the output. Now, what we do here, and to ensure, so there's 3 3 S-curve segments here, and this is the jerk limited one. So we've actually we're only moving by 1 meter, and so what we're limited by here is a curve that is limited by the ability of our aircraft to roll and pitch fast enough to follow that curve. So we have to go slow enough such that our maximum roll and pitch rate is not exceeded. And in that case, it's a maximum jerk of 10 in this example. And you can see that during the fastest acceleration changes, the jerk gets up to 10. And other than that, it sort of does a pretty good job trying to maintain the maximum velocity and acceleration it can around that curve. Again, the curves look almost identical. They're not quite. Some of the limits just move the curve around a little bit compared to the previous one. I should have actually done all 3 on top of each other at the end so you can see the deviation with the different limits. But it's a very similar curve to, when you look at it. And now we're maintaining acceleration limits. Now, the way we do this is we actually, based on the geometry of these 3 vectors, we define the S-curves with intelligently chosen limits to begin with. And then we shift the timing of each of these limits so that as the accelerations from 2 consecutive segments are actually both coming up at the same time. If they increase beyond a certain point, we delay the second one a little until the sum of the 2 accelerations don't exceed our limit. And so we're able to do that very easily and with very low computational cost as we actually move through. And this is a nice large 100-meter spline segment there where we're velocity limited. And you can see here we're getting up, we sneak just over a little bit here, but it's sort of only, 5% or less, and we can actually do that a little bit better moving forward too if we want. We do a very, we do a good job of sort of maintaining our maximum velocity, except for where we are in our corners and experiencing strong lateral acceleration, where we slow down for those corners a little bit. Now, this isn't completely optimal, but because at every single point on this line, we know exactly what position, velocity, acceleration, jerk, and jounce is, we're able to further optimize with a look ahead algorithm moving forwards if we want to get the absolute best performance along that segment. So, advancements in looking forward to 2020. Hopefully we'll start making a lot more use of the ESC telemetry and ESC feedback to optimize our motor mixes and the performance of our motor mixes and our motor loss handling. It really, because if we know, not just think or guess, but know what an ESC does, it provides us additional options in how we handle that, and we may even be able to do much more significant change in our motor mixing to get a more optimal performance, or perfect handling of motor loss. Automatic dynamic harmonic notch filter, the FFT driven stuff that I was talking about earlier, that's going to be a significant, there's a, you need to know what you're doing setting that at the moment with the current throttle based thing. You need to do an FFT, where this potentially allows automatic settings to work very well. FFD and the general feed forward work and delay stuff that Bill and Josh have been working on and or working with me on, with the attitude stabilization loop delay aspect. So that's quite exciting stuff, but very much experimental. Now, the yaw rate angle command. Now, that's something I didn't quite touch on before, but basically at that coordinated turn, this becomes really important for coordinated turns, because if you just have a target angle, the actual angle always delays it, because when you're producing a target angle, the actual rate of change is proportional to the angular error. And so this allows us to actually feed a rate and a target angle into the into the yaw controller, and the target angle stays precisely on the actual measured angle, because you're also feeding this rate in there, until the rate exceeds your maximum rate, in which case you hit the limits, and those two things come apart, because the attitude controller can't maintain your target rate. However, when you actually slow down again, where this can catch up, it very smoothly catches up to your target position. And it's that model that we're also looking to use in guided mode. Position controller rewrite, to bring that up to implement all our learnings from the attitude controller into the position controller code and control laws. Fully support ECAF resets and things like that, cleanly and twitch free. The guided mode stuff that I've just been talking about, and the trigonometric S-curve based waypoint navigation. There you go, Josh. Give Leonard a clap. I get shit about this all the time. But anyway, so that now I think is pretty well ready to go in, and so there's a bit of work to do over the next month or so. But hopefully by end of March we'll actually start being able to put that into, like, actually put a PR into master or something like that. So sorry, not March. Another month or two we should be able to actually have a PR into master. But yeah, so that's my talk. 4 minutes over time.
Absolutely brilliant. Thank you, Leonard. Really fantastic. I think we could have a few minutes for questions. There's been a great commentary going on in the chat. Some questions there. So, does anyone have any questions for Leonard?
I can start with a small question to learn something that you discussed about strategies to auto-tune, because the current strategy to auto-tune is to get the vehicle perfect. But sometimes for certain payloads, we need the vehicle to be, let's just say, sloppy. So we have to auto-tune it and then detune it to get the behavior that we want. When you mentioned the strategies, it is something like that you were thinking of?
No, absolutely not. That is fundamentally not the way to tune up an aircraft. It's one of the things that so when you're coming from a classic control background, especially people designing, you know, high-end equipment, what happens is your dynamics of the vehicle is directly dependent on the tuning of the vehicle, and they're both one and the same, because you tune the vehicle with your high-level control laws to get the handling that you desire. Because we operate in so many vehicles, we have evolved to a state where you have a tune for your aircraft that is the optimal disturbance rejections, sharp as a razor, if you can get it there, depending on your aircraft, tune. The absolute best tune you can get, there's really sort of two key factors you can tune for: maximum disturbance rejection or maximum response, and they're about 5% different in your tuning value. So, you know, but that's well within the error bounds of most people's tune. And then there is handling and feel. And that's why we have the input shaping parameters and we have our tuning parameters. So you always tune for an optimal tune, that's with our error bounds covers maximum disturbance rejection or maximum response. So, you know, I feel confident to say optimal tune. But then you say, oh, but I want it to handle like a Cadillac, not a race car. And that's where you go into the input shaping parameters, and that defines your maximum accelerations and lean angles and the jerks, on your attitude controller, which is your time constant there, effectively. And that's what defines the feel of your aircraft to the pilot, and how it actually moves in the sky and how it looks when it's navigating. And so you can slow that down there. When people have used much simpler tuning, control setups where your performance was based on your PIDs, the way the aircraft flew and felt and reacted to your sticks was based on your PIDs. People had to detune to get the softer performance that they wanted to achieve. But that's a thing of the past. Now you tune up, get the best tune, and then make it fly however you want, completely separately with a separate set of parameters. The key ones being the maximum acceleration, the time constant, and the maximum lean angle of the aircraft. So auto-tune focuses on just the tune and getting the optimal tune. And then we still need to train people how to get, after they've done that, how to get the feel that they want. When I do an industrial tune, a big part of the process, I can get a nice tune, but then the question goes to the client of, okay, how do you want your clients to interact with this aircraft? How do you want it to feel to your client? What sort of response time? And most of my clients with these big aircraft, it's sort of like, okay, I want it to handle like a DJI aircraft. Okay, like really soft and docile, but without the wobble around all over the place crap. They're getting better, but anyway, I had to have a dig. I don't touch the tuning parameters to do that. I go back and define maximum rates, all the input shaping parameters that we have there. And that tuning guide that we put up actually goes through that process. And at the end, it sort of says, introduces people to how to get the feel that they want out of the aircraft.
Hey, Leonard, this is Bill. Hey, that's probably true for multi-rotors, but for helicopters where we use a feed forward, we'd probably have to readjust the feed forward, wouldn't you say, if we change the
absolutely not
our model?
Absolutely not.
If we've
the problem, most of the heli users are still most heli users have not learned to tune up their helis yet, and they're still having strongly coupled tuning parameters. Like most of them have actually effectively turned off their input shaping and dealing with poor tunes. But no, for helis also, that structure is very firmly placed in the attitude controller. In that this holds true for all aircraft running that attitude controller, no matter what your tune is. If you've got a good tune with your feed forward, such that your angle target is matching your angle request, the ghost and the actual are staying on top of each other, what I said holds 100% true, no matter what.
So from what you're saying, I believe that you're recommending helicopter users to start using the auto tuning?
No, because we haven't done auto tune for helicopters. But helicopters are really challenging things to tune. These, you can't use auto tune because auto tune isn't set up for helicopters. So absolutely not. But helicopters, and Bill, I'm sure when you watch Bill's presentation, you'll get a better appreciation for this. But feed forward is pretty easy to get right, But the PID terms, there are a few quirks that I'm sure Bill will go into more detail with, that mean that tuning up the PD terms, P in particular, with what I've seen. Can cause an oscillation. You get tiny values on some aircraft for P and D, depending on your filter settings. So helicopters are actually really difficult to tune properly, and therefore when you've got a shitty tune, and most people don't even know how to do a basic tune, much less solve the problems that they face. Then you're not keeping up with your attitude controller requests anyway. You've got this thing that's wobbling around and not following what the target is. So helicopter, I'd like to see if we could get auto tune running to get the, if we can get the auto tune running where we can actually automatically set the feed forward. That would be great. It's going to be really interesting to see how auto-tune, like a rigorous system like auto-tune, handles the PID stuff. And I suspect going through that process with helis, we'll, like we did with multi-rotors, we'll learn a lot about how to get the most out of that tune. And then we'll start seeing consistency across the helis, because at least they'll all have the right feed forward values. And their yaw will actually get a decent tune in there. Roll and pitch, we may have to play with filter settings and notch settings to get the most out of the actual PID settings. And Bill will probably talk about that later. So heli's got a little way to go before it reaches the same level of consistency and that sort of stuff, where we can make it easy for users to separate the tune from the handling.
Hi, Leonard. Emilcar here. One question. You said that the I term should match the P term. And that sounds kind of strange to me. Can you elaborate a bit why the I term should be the same thing as the P term?
Now, this is specific to multi-rotors. Now, the reason for that, now it's I equal to P for roll and pitch, and I is 1/10 P for yaw. And the reason for that is so increased I term is increased overshoot when you stop. So we don't ideally, if we could not have I, it'd be 2 thumbs up. But we need I to take out our offsets and our constant things. Now, one of those key ones is propeller flapping torque. When you actually lean forwards with your multi-rotor, you get a propeller flapping torque, which wants to basically turn the aircraft into an umbrella and make it flat back. So as you speed up, you need to create more and more constant forward pitch through the I term to actually maintain that attitude. In fact, you can limit the maximum lean angle of a multi-rotor by limiting Imax, and it won't be able to push past a certain lean angle once it gets up to speed. So when you do that, you lean forward, and then the aircraft sort of tends to, as it speeds up, it tends to lean back as the propeller flapping torque builds up, and then the aircraft leans forwards as the I term builds up, and then you lock into that target attitude. Having a P equal to I gives a time constant that is pleasing to the user. And so generally for smaller aircraft, you don't need to go bigger than that and actually get a pleasing feel for the user. But if you go smaller than that, you start to get a noticeable where it leans back as it speeds up, and then it has to fight forwards back to the thing, and it feels it doesn't feel confidence inspiring and nice. So values of between 1 and 2 times P tend to work really nicely as far as keeping a minimum I term and minimum overshoot, while keeping a constant disturbance rejection reaction time that is pleasing to the user. For very large aircraft, the I term starts to oscillate, and you start needing to bring that I term down to half P to a third P, and those sorts of numbers. Does that answer your question?
Yes, perfectly. Thank you very much for the detailed information. But it would be nice to add, especially the last part, to the wiki, because we're flying with big copters, and we're seeing that we need to kind of reduce the I term a bit, and it's not on the wiki. It would be nice to have that last sentence that you said. That
what do you mean a big? What do you mean a big copter? What's your idea of a big copter?
And it's 1 meter diameter.
That's not a big copter. When I say a big copter, I've had to reduce the I term on aircraft over 150 kilos.
All right.
So I haven't had to do that on aircraft below 100 kilos. So I'm not saying that you don't have to on your aircraft. I'd have to have a look at that. But you're saying you're getting oscillation in I term.
Yep. Yes.
Right. Well, every aircraft different. So that's perfectly possible. But it may be because you've got another tuning problem too. I haven't actually seen that on smaller aircraft of 50 kilos and less.
Thank you.
But yeah, I'm happy to talk about that and have a look at some logs if you like.
All right, so that's absolutely brilliant, Leonard. Fantastic talk. So if anyone wants to unmute themselves and give Leonard a round of applause.
Yay.
heckling in private chat.
Fantastic.